Thank you all, and thank you Aegis, Chairman Sir, for giving me the opportunity to talk at this event. And thank you Aegis again for organizing such an event at scale in India. And I think this is the first event that I've seen at this massive scale wherein all the industry leaders are here to talk about their experiences. I've been in SAP for quite some time and worked with a lot of Fortune 500 companies. And I thought it would be interesting for me to share some of my ideas around massive machine learning and the notions around that, and the challenges that we go through when implementing machine learning at scale. This is the outline of how I'm going to talk or structure my discussion. Analytics continuum, it is very necessary for us to understand when you talk about analytics, what are we exactly trying to talk about? There is a gamut of things that are possible into the entire value chain of analytics, right from curating the data, collecting the data into your data warehouses, creating interesting dashboards, and eventually having predictive as part of the workflow. So when we look at analytics continuum, is there an analytics continuum? Is the question that I would want to answer there. Take you through the notion of what is massive in machine learning implementations, build up the case there, and then talk about challenges that we see when we start deploying machine learning at scale, with some examples of our customers who have deployed machine learning at scale. This is going to be a challenge today, I think. Okay. This is not a new chart. If you Google, you'll find this chart. And I think in many conferences, not even here, but outside, this is how the entire analytics continuum is discussed, or at least talked about. You start from the raw data and then reach up to prescriptive analytics. But you should see the title. I'm saying that there is no such thing as analytics continuum. And I'll put my case here. Why do I say so? So if you're looking at the left-hand side here, oh my God. On the left-hand side, before the charts, we have data that is available to us, aggregated in some form, for businesses to make sense of it. Okay. This particular journey has evolved based on need of the customer. Initially, there was data which was all segregated in different landscape, and there was a need of IT to get into that, structure in order to ensure that there is coherent view of data across the organization. So then came the notions of getting a data warehouse where you are curating all the data, putting it together for businesses to then create charts or create aggregations on top of the entire data's landscape to understand what is happening with the business. So here, whatever is the output of this BI kind of analytics is for humans to make decisions. You actually aggregate the information, you provide dashboards, humans actually interact with those dashboards, play with it, and eventually understands what is happening with my business, what parts of my business is working, what is not working, and then base their decisions based on what is available in the data. Second point here is that data is aggregated for visualization. Nobody in business wants to understand how one customer of theirs has responded to a specific event, and that event could be reaching out to them proactively, or whether the person has opted for an offer or not, whether the product launch was successful or not. For them, it's like, I want to look at how my business is doing in the last few months, last 1 year, whether it is growing or not growing, and then ability to go slice and dice the data on an aggregated format. Right? So the point of interest here is aggregated data for visualizations. And how are these data points provided to the users to consume? These are always on an UI level, right? It's more about creating those interesting visualizations or part of your dashboards, which are continuously being refreshed based on new incoming data, but again at an aggregated level. So this part of the presentation here, till agile visualization, is all about allowing humans to make decisions based on the aggregated information, and the interaction or the technology that enables them to do that is integrated at the UI layer. Now let's go into the other aspect of it. When you look at predictive analytics, and again, there are, the world of data science is full of jargons. Sometimes you take it as predictive analytics, then machine learning, and then advanced analytics, and so on and so forth. So there are a lot of terms that would be interchangeably used here. But what is predictive analytics trying to do here? Here, the idea is to have machines to propose or make decisions. When I say machine to propose is that there is an algorithm that is able to look at several thousand options or several thousand decision points that you have to go through, and eventually present you with 3 or 4 most important, strategically important directions or business directions that you might want to evaluate, rather than going through that 100,000 different options that you have. So it's trying to reduce your choices to the most probable choices that would eventually succeed, right? So here, it's machine proposing for the humans to take decisions. So it is like helping the humans to isolate their problems and eventually narrow down to the best possible pick or best possible picks from the set of choices that they have at hand. And on the other side, it could be, oh my God, that's okay. On the other side, it could be that machines are proposing the decisions and also taking them themselves without any human interactions. So you look at autonomous cars and so on and so forth. You have machines which actually use this data, mine them, apply an algorithm on top of it, and then decide what it needs to take as the next logical step without any human intervention. In order to do that, as against how BI or BI kind of analytics were, we are not looking at aggregated information, because behavior of each entity in your transaction is very much important, and each person or each entity in your data landscape has something which is different from the other person. So in predictive analytics or in machine learning, the most important aspect is to go and look at the most granular level of information. So from aggregated information, which was more for BI dashboard reporting, you are going into highly denormalized set of data. It has to be flattened because, again, we know that in data warehouses and others, you have cubes which enables you to actually query those data and do all the drilling down and drilling up at a significant pace because of the way data has been structured. But for machine learning implementations, you need to flatten that data and reach to that granular level of information that allows you to understand the changes in the behavior of the entities that you're trying to evaluate. The next difference is, it is process integration at least. In BI, the interactions was UI. People had flexibility to go drill down and drill up. But predictive is most powerful when it is embedded into all your business processes seamlessly without an UI. Yes, data science implementations do have maybe a scripting UI wherein you are able to script your algorithms, or maybe you have a drag and drop kind of a canvas that enables you to have complex pipelines. But that is not the actual value of data science implementations. It's when every part of your business that is impacted by any interaction that the customer is having with your ecosystem or with machines that are actually impacting your processes that are influenced by the outcome of the predictive seamlessly without you intervening with it. So it is process integration at least. And the additional part or the additional dimension of any predictive or a machine learning implementation is that it generates data. In BI landscapes, when you're trying to aggregate information, there is no additional data that is formed in addition to the data that is available in your data warehouses. But in machine learning implementation, the amount of new features that you generate by virtue of feature engineering in order to capture the behaviors, the changes of the behaviors of the customer or the entity in interest in your data actually enables you to now look at maybe 100,000 new data points that are curated from the original data set itself. So now looking at both these aspects, there is no continuum because this is completely different. It is aggregated for visualization, and there you are actually doing completely opposite. You're not aggregating it. The integration is at the process level, right? It is highly deflattened, and again, it also generates huge amount of data volumes. The challenges in each of these aspects are completely different. But if you're looking at The same slide, if I look at from a different perspective, if I'm looking at the maturity of the organization in this data-driven transformation, yes, there is a continuum. And the continuum is the maturity of the organization in the path of making their organization completely data-driven. Oh, thank you very much. Now, this is another aspect that is important for us, though it doesn't fit well in the presentation. But I thought it is important, and I'm not wanting you to look at the exact numbers here, but the intent that I'm trying to convey. We know that BI analytics and visualizations and the part that I spoke about earlier contributes towards a $10 billion kind of a market. And it's also growing, but it's not growing at a pace at which the advanced analytics, predictive analytics market is growing. There are various aspects of the query reporting and visual analytics that are growing at a negative rate as well because of the changes in the technology and the demand that is there. And the very fact that we are gathered here is because of the changes that have happened in the market. And this particular area of advanced analytics and also about unstructured is growing, and it is growing at a significant pace. The aspect that I want you to look at is the ratios here. As a company, if I am investing X amount in the BI landscape, and if I am not investing 1/3 of that BI investments into predictive, I'm already losing out. Because there are several thousand companies in the world who are actually ahead of the curve, investing significantly higher in order to change their businesses into completely data-driven organization. So let me build a case for the massive machine learning implementation. If you look at all these bubbles, right, except for the last one, these are various aspects of any business, be it BFSI, and we heard a lot of interesting discussions just before my talk here. But if you look at the use cases, and these are some of the use cases that our customers already have in their landscapes. Look at sales and marketing. You have churn reduction, customer segmentation, lead scoring, and so on and so forth. This is a sector that has significant implementation of machine learning into that aspect of business. On the other side, look at finance and HR. One specific use case of cash flow forecasting. According to the US Census, in US, there are around 1,000 companies that get formed, new startups. But there are double the number that actually go out of business in that same year. That means there is a declining growth of new startups that are coming in. Why so? The main problems that were identified by Howard was that these startups who have failed because of cash flow management. And predictive can help significantly. And one of the use cases that SAP has in this area is, and which is integrated into their S4 application, is contract consumption. I, as a company, have several contracts that I negotiate with my vendors. And then I want to understand when these contracts are going to be consumed. And if I know that these contracts are going to be consumed before the expiry of the contract, there is a way by which I can renegotiate these contracts much ahead in time. Second, because I'm already predicting that these contracts for X number of laptops or whatever is going to be exhausted in the next maybe few months as compared to the year that it was negotiated on, it also helps customers to have business continuity because they are already aware that because of the changes in my application, there is a high need of me to then renegotiate and then ensure that these things are in lines for business continuity. On the other side, when are my invoices going to be paid? This is another aspect of finance that is very much important because you have a lot of customers of yours, you raise those invoices, and these invoices are paid out at a future date because of various different contract negotiations that are happening. If there is a way by which you're able to predict whether these invoices are going to be paid on the committed date, and if there is any reason why these invoices would be delayed as compared to the committed date? And what are those influencing factors that drive that kind of a behavior for specific customers? Then I can build my business processes around that to ensure that I have healthy cash flows that I can manage. A good other use case in HR was everybody talks about gender diversity. And it's proven by various leading organizations that a 2% increase in the gender diversity ratio actually has a 10% increase in the top line. Now that is the impact, and many big organizations have started to look at this thing seriously. But how do you ensure that, right? And there is one use case that we worked on, which actually starts at the core. When I create my job description, do I create the job description in a manner that actually drives away a male or a female from applying for the job? Gender diversity starts there, right? So how do I make it more generic? How do I assist the manager or the recruitment manager with enough information about the JD when he's creating, saying that this is more biased to the male or the female, and also propose different terminologies that can be used in order to make it gender neutral. And so there are several of these there. Now look at one aspect, and the most significant aspect would be coming from sales and marketing. For example, a global organization which has several thousand products, sells in several different countries, via several different channels to various customer segments. Now, if I want to have an offer to be targeted to a specific customer via a specific channel for a specific product in a specific geography, I need to create a model for that. We know that there is nothing like a global model, right? I build a model for the entire universe and it works for everything. That never happens because there are nuances in each of these aspects that we look at. And this one simple use case of targeting my user via a specific channel at a location where he is for a specific kind of a product, that one use case is looking at several thousand models already. And when the organizations are going through that entire digital transformation journey, every aspect of the business has such several thousand models. So it's not that you create a model in an isolation in a lab and you deploy it. And if these models are going to impact how business is going to be done tomorrow, then you might as well be very careful as to what you're doing with these models. And that are the challenges of massive machine learning. So this notion of massiveness comes because every organization in the next 5 years, and most of them, would want to have predictive as part of any data point that is generated by human interaction or machine interactions with their system, with their businesses. And if I'm looking at this massive scale of deployment of machine learning algorithms, we are looking at a complete shift of how businesses are going to change the way they function. There was an IT department revolution the moment you had computers, connected networks, and everything that came into place, wherein it was needed that there has to be an organization and an IT strategy for every businesses so that there is a coherent view of all the business data that is getting curated in order for the large enterprises to have a single source of truth for their organizations. Same is going to be the case here. When we talk to customers, sometimes the IT department has the data scientist role in their organization. There are some institutions wherein the business division or the business division has the data science role in them. But it's going to be even challenging here because if you are looking at machine learning at scale, this means that this particular initiative has to be driven top down. There has to be a corporate strategy around data science and an organization that cuts through all these different layers and collaborates with each of these stakeholders in order to ensure that the scale at which customers are trying to embark in the journey of digital transformation is actually realized. So there are two aspects to this notion of massiveness that we are talking about. One is that there has to be a way by which you are able to look at several thousand models that are influencing your business in a single cockpit, or at a specific setup that enables you to evaluate these models in runtime, because we know that whenever machine learning or any predictive is interjected into the normal flow of business, the data that is captured after that is already influenced, has changed its behavior. So it's not that you have one model that lives for life. This has to be monitored continuously. And if these are seamlessly integrated into business processes, then you need to ensure that these predictive models are at a stage wherein you can trust them and eventually monitor them with strict governance in place. On the other hand, predictive for the masses. When you're looking at predictive, and if predictive is seamlessly integrated into business applications, every person who is interacting with business is a consumer of predictive in some ways, right? And the massiveness or the scale at which that changes the interactions of the customers with your ecosystem is also significant. And these are the two notions that has to be tracked by an organization in order to embark on that journey of digital transformation. My God. Okay. So cautions. When you're looking at machine learning implementations at scale, it's not simple, right? There are challenges. And there are challenges when you are actually looking at deployments at scale. And there are parallels with what we already know. We are, in some sense, touched software or writing code or writing enterprise software applications. And these are the various notions that you look at when you look at software, right? And this actually looks at the debt that you create while creating these enterprise applications. Debt is good, right? Debt is good because you take a choice not to do something in order to deliver innovations faster to the market. But in doing so, you are actually creating something that needs to be addressed as soon as you have time to do so. Few things are visible. So if you look at the visible aspects, if you are launching a product, then if there are missing features, the customer will see them. So these are debts that customer already knows about it. As a developer, there is another aspect. The defects or the low quality of the product is also visible to the team. The things that are not visible are the things in the center. The shortcuts or the workarounds that you take because of architectural decisions, right? The things that, because of not adhering to the software engineering practices, you don't use the proper design patterns in order to reduce the code complexity. Or you create a lot of technical debt in the code that cannot be managed or serviced. Now, these things are not visible to the end user. And at times, these are the ones that are very costly and very dangerous for any organization if they want to change or adapt to the fast-changing requirements of their end users. Now, I would want to translate these into machine learning implementations. Because the moment you have machine learning implementations, again, machine learning is also a piece of code. And that code also has these limitations underneath, these technical debt. But because machine learning also depends on the data, the debt that you create by either knowingly or unknowingly creates even more challenges as compared to the software debt that we see here. Scully et al., a researcher in Google, and it was interesting to read his paper, and these are some of the thoughts that he's put into that paper. I think every data scientist, when you talk to him, they'll figure out, oh my God, I know this. So the only thing is Scully et al. Has put it into a paper, right, in a beautiful format so that people can look at it. So as the machine learning community continues to accumulate years of experience with live systems, an uncomfortable trend has emerged. And what is an uncomfortable trend? That it's easy to develop something and deploy it. But when it comes to maintaining it, there is significant pain. Now, why do I say this? Because when you do a POC within your organization, when you're able to get some success there, you talk to the business, you convince them, they find success, then there is nothing they would not want to wait. Is it ready? Can we put it into production? Can we go target? Because we are losing time. We have lost, if you say, I want 1 month time to actually make it better, more seamless, integrated into business processes, they'll say, "Arey, 1 month? What are you talking, man? I'm already losing money and I'll lose more." Put it into production, right? And this is what is happening. And when all those siloed things get into production, that generates a lot of technical debt. And Scully et al. Has put together significant laundry list of things that addresses that aspect. This thing is somehow not working. His paper is big, and I have provided references to this particular presentation here. But the common trends that you see are categorized into these wide buckets: feedback loops, anti-patterns, changes in external world, extensive data dependencies, configuration management, and boundary erosion. I'll provide some examples of each of them just so that you get a feel of what those debts and those significant challenges that we have when we actually deploy machine learning at scale. So look at feedback loops. So just for example, if I'm looking at placing specific ads on my web page based on user interaction, right, in order to maximize the hits on specific offers based on customer profile. Now, this is a significant use case there. That means I'm trying to optimize the ads that are going to be placed, and I actually then auction those spots in that web page for maximizing my return on those investments. The various aspects that you look into as features are: where did the user click, what are the things that they clicked, and so on and so forth. You curate that historical data, you build a model, you find that yes, you get significant lift, you put it into the application. What happens next? The next possible behavior is you are now intelligently providing the right ads to the right people, and so people who used to click somewhere else are now starting to click at the recommended contents that you are actually providing, right? So the behavior has changed. And when the behavior has changed, this particular interaction, when again learned at a later stage, you don't get the behaviors that you had actually started with. So the models and the assumption that you started with has completely changed as compared to when it was post-production. Now these are not modeled inherently at the start. So things do change there. There are several examples in the paper, but I'll just touch upon a few of them there. When I look at boundary erosion and complex models, if you look at, and if you have studied databases, you know that it was very necessary for you to normalize the data so that the various problems of databases like redundant information, it's get updated somewhere and it's not reflected somewhere else, and so on and so forth, is already put together as best practices for you to build those data. But what happens when you are looking at machine learning implementations? You want to have a fine-grained information about your entity. And this entity has touch points across this normalized data sets, right? So you are looking at, for example, if I want to recommend an offer to the person, I will have his past interactions in some transactional database. I have his own demographical information in some sense. Then the things that he has bought from me in the past is managed in a different sense. How does he pay is managed in a different sense. This is highly de-normalized. But then when I actually get a machine learning implementation, these normalization go for a toss. I actually get everything in a single source of truth for that entity and then build. So there is a boundary erosion already. So what happens if something inherently changes? Maybe the data structure changes, maybe you have new information in the data, maybe you have acquired a business and you have to adapt two businesses together. What happens? What happens to your machine learning implementation if not tracked? And if you're not aware that these are the things that have been consumed by a data application, then there is a problem. On the other side, if you look at code, there are design patterns that enables you to structure the code with various abstractions so that it is extendable in some sense without significant effort. But when you look at machine learning implementations, where are those abstractions? does a data scientist, when he actually builds an application or a predictive model, does he think about all those concepts? It's difficult. Is there a way, and the question that has been asked is there a way by which we can respect these boundaries in the data and still create a model? Can we create simple models for each part of the data and then work on it? Yes or no? We don't know. Changes in the external world. Again, and I think with many panels yesterday and today, and many discussions, we look at structured, unstructured, this data, that data. There are many other open data sources that are available that can actually enrich your data models and so on. But at an enterprise level, when we are actually looking at so many external information, curated into your system, and then used as part of your machine learning application, you are not in control of the data that you're consuming. And the people who are generating the data do not know that you are the consumers of these, right? So it is not necessary that when they change the way they get the data, capture the data, if they change something there, they're not even bothered who's going to consume it because they are not aware of it. So unannounced consumers of external data, or it could be your internal data as well. For example, I create my models and I have generated beautiful scores, risk scores, propensity scores and whatever, and I have it as part of my data. Somebody in business has access to some of these data points. He looks at it, he creates a beautiful dashboard and finds, oh my God, I don't know where the number is coming from, but when I look at this number, I'm 100% sure that if I go target this set of customers in this manner, my business is going to grow twofold, or this is a new market for me. He builds a process around it. I did my model, I generated those scores. I don't know that there is somebody out there who's actually using that. Why? Because the notions of who is able to access what is very much well defined in the BI landscape. Only with access authorizations and the roles and responsibilities it's able to do that. But when it comes to predictive, are there processes that enables us to do that? Again, this is another way of looking at the world. Expensive data dependencies. Expensive data dependencies also ties to the example that I gave, is my scores have been, so I build a model, and there is some slight change in the business problem, and they say, okay, I have a model that addresses one aspect of this particular problem, and there is a delta that is not, or a residue that is not trying to explain. I'll take the inputs of this model and create another model that understands only that delta. Okay, so I took the model and I enriched it with another model that explains the delta part of it. Business change, customers change, interactions change, there is another delta that is created. Now what you have done is you have created cascaded models because you do not want to start with a global model altogether. On the other aspect is, if I have features that I had started up with, I'm using in my model, and I have this model which is evolving over time. As I said, the moment predictive is part of the workflow, the way users interact has changed. And that also changes in the quality of the features, or the features that have now new explanations of the entities in question. So now what I do is, okay, there was something which was working, I have new information, I create new feature engineer, but I do not bother about those features that were initially part of the model. I keep it because it's not harmful. I go ahead. When I do so, there are a lot of such features that get into your system because of these cascaded behaviors, which are not costly at the start, but when things start changing or the distributions start changing in those unutilized features, it may impact your business significantly because the scores can be impacted as well. And there are several such instances there. Common anti-patterns, and this is predominant. This is predominant because every data scientist has his tool of choice. And does he want to align with the organization's tool of choice? No. Why? Because it would be either the IT VP who is taking a decision, or it could be the business head who is taking the decision. That, okay, this is the organization alignment, and this is how we want to do that. So everybody has their, again, I don't blame the data scientists because there are problems that can be specifically well solved by different technologies. So there is no harm there, right? So something can be done well in Python as compared to R or as compared to any other technology there. So there is a mix of open source as well as industry software. But what happens is when different groups work in silos, and come out with specific parts of these problems addressed by different technologies, when it is inherently presented to the business, they want, okay, can we not do this? Oh yeah, this is working for you. This, okay, then what we do? Let's put it together. And this putting it together creates a lot of glue code because these technologies don't talk to each other. So I have to some way make them talk. And I do all those bandit treatments in my entire application that creates a lot of dependencies. And if I now want to change something, that is not possible. So those are the kinds of, again, I don't want to get into a lot many details here, but this particular, there are 3 papers that has been written by researchers in Google. The impact of technical debt in or hidden debt in machine learning implementation has been brought out by these two papers, and I think possibly you would have heard of this. Google used machine learning, that is textual information, to predict the rate of influenza. Okay, and it was perfect. And what they used was the keyword searches, the searches that the people did at that point in time in order to understand whether they were infected by influenza or not. And this was an epidemic at that point in time. And they were able to predict with significant amount of confidence, 95% confidence in up till 2008, as compared to how the Center for Disease Studies actually recorded those cases. It was in play for a long time, and I think around 2013, the journal on Nature came out saying that, oh my God, Google is actually completely wrong. It's predicting all those cases significantly wrongly. What happened? And the various aspects of hidden debt are examples of why that failed. The person who created this algorithm actually optimized the algorithm significantly without knowing that it is used by this particular application. The searches, the search mechanism, as well as the text to feature extraction logic, the data feature engineering logic changed significantly for optimizing the searches all across the Google product. It also impacted this. There are other aspects that impacted this was that there was swine flu, and there was another flu, kind of a flu, that was also part of the disease epidemic during that time, which was not captured at all, right? Because there was no interaction and there was no proper governance around that, this particular paper came into play saying that what went wrong. And I think this is an interesting read in order to understand the common technical debts that there, here, I don't know. Okay, so I'm almost towards the end. These are a few interesting papers around technical debt that you might want to read. It explains even more than what I have actually discussed here. One slide on what we are doing. We are doing a lot of stuff. SAP is not known for machine learning. It's more for enterprise applications and so on and so forth. But we have a wide variety of stuff that we do within the organization, right from enabling somebody to manage all these models at scale to technologies on big data on-premise and so on. And we also have technologies that enable somebody to seamlessly embed predictive as part of business processes without stopping the business, right? So data is in motion. So I'm sure I'm out of time, but I'll just take you to the last slide. These are the various examples of how machine learning has been implemented at scale. And I leave you with possibly 2 thoughts here. Right? Asking the right question is very much important, right? Having the data and having an itch to find a solution doesn't necessarily mean that you're able to solve that. And an approximate answer to the right question is far better than having a right answer to the wrong question. Right? So thank you, and I leave it. I think I'm exceeded on time significantly, and I'm being told there is no time for questions, I think. Yeah. But anyways, I'll be around, and possibly we can have some discussions on the corridor as we go. So thank you for that.